full screen and then try again?
Yeah, I'll just try.
And does
Yeah,
it work?
it is
Yeah,
visible. Yeah,
it is
yeah,
working. Yes.
yeah. Thank you very much. I'm sorry for this one. I wanted really to attend this in person, but somehow at the last moment, my health. And I start before I start my talk. I want to say a few words for Professor Pa. I always admire your excellence in teaching, administration, and contribution in theoretical chemistry and condensed matter, sir. And wish you all the best, sir. And I dedicate this talk to Professor Pa. Plan of my talk: the first I'll discuss about the motivation, and then I'll talk about the few frustrated spin model systems, and I'll talk about this the quantum phase diagram of this spin model system, and then I'll talk about the modeling of magnetic material, copper germanate, and this metal organic compound. So uh, this is copper germanate, and you see here this is a three-dimensional system, and however, the effectively this act as a 1D spin chain. If you see the blue atoms, the coppers, this is along the C-axis. If you see, it forms a chain. However, the distances along the other C and A direction, it's quite large. So effectively, the spin exchanges are restricted to only 1D. So here the magnetism, we are interested in the magnetism. So most of the magnetic contribution comes from the copper. So like, let's see what are the experimental result we have. And you see here, I'm showing the CV here, and you see there is a sharp anomaly at this point. Uh, okay, point. Okay. Sharp anomaly here, and that is around 14 Kelvin. And this is June version of at this point. I mean, you see that there is a sharp. I mean, it almost looked like there's a 2D behavior, but actually it's not 2D, but something else. It's sometimes it is called also lambda transition. Uh, and the entropy is also shows discontinuity at the same temperature. Uh, Here I'm showing the magnetic susceptibility, and you see the magnetic susceptibility also changes abruptly at 14 Kelvin. And below 14 Kelvin, the distances between atoms are not same, or actually it behaves like system is dimerized. And that's why we call below this temperature, there is some sort of a spin spiral transition. This is generally known as a spin spiral transition. Uh, and in fact, below this temperature, if you see, then your atomic distances are like sort of like uh, long, short. So your spin exchange also supposed to be like having high and lower values. Okay. So the another signature of this is found by the inelastic neutron scattering data. If you see here, you see the beautiful dispersion curve of this material. And here we are showing you the ST gap as a function of temperature. And you see that the ST gap is varying with temperature, and it vanishes around 14 Kelvin. Again, it's the same temperature at which your anomaly is. And so this measurement, the singlet triplet measurement shows the inconsistent, there's no consistency with the existing theory. And dispersion relation is also not well understood. So what is the current understanding of this material? The system is modeled as a spin chain with a model having the J1 as J1 is a nearest neighbor exchange, whereas J2 is a next nearest neighbor exchange. The prediction is the ratio of this J2 by J1 is approximately 0 to zero point 0.3. In fact, many people have, I mean, various theories predicted from zero point 0.2 to 0.35. Most of the theoretical calculation explains only the high temperature data. The low temperature below the spin spiral, mostly it's restricted to the mean field level. The gap measured by the inelastic neutron scattering has not been explained by these theories. Second material, we are going to take this metal organic compound, and this is again three-dimensional system, and it is a three-dimensional donor acceptor system with TTF as a donor and bis dithelium metal complex as a acceptor. And TTF, a plus molecule, is have a one unpaired electron and sticks along the C direction, which is perpendicular to this line. The pi conjugation between the TTF plus is confined along the C axis, and it also behaves as if you have a 1D spin half antiferromagnetic chain. And here I am showing the magnetic susceptibility like a 1D spin chain at high up to high temperature, and you see that there's a kink here, and this is around 12 Kelvin, and below this there is a SP transition, and the high temperature part can be fitted with the one-dimensional Heisenberg simple Heisenberg spin half chain. Yeah, and the most of the this SP transition, I mean spin spiral transition, are frustrated spin half system, and this cannot be solved exactly. Even the, I mean, if you take this Heisenberg normal antiferromagnetic Heisenberg chain, and if you dimerize it, there is no exact solution for this. And I mean, even the ground state have a problem. Uh, like if you want the thermodynamics, then even simple HAF have a problem in getting the thermodynamics correct. And all of us know that numerical calculation have the finite size effect at low temperature, and so what we'll do, so we are going to, we have recently developed the hybrid DMRG method, which gives a very accurate result at all temperature for correlated system. I'll not go into details of this method. Probably if someone is interested, we can talk about it. Oh, again, it has frozen. Sorry. Sorry, again, it has frozen, I think.
Maybe just escape and try
Yeah,
again.
that's what
Yeah.
I'm doing, yeah. That's why I don't like. Yeah. Okay. So let's go to the frustrated spin, 1D spin chain model. And here I'm showing you that you have the one-dimensional arrangement of the spins. You have nearest neighbor J1 and you have next nearest neighbor J2. And both are antiferromagnetic here. And you see that below some critical limit, you can have uh, this all spin up antiferromagnetic system, antiferromagnetic arrangement. But if you increase the J2 below or up to some critical value, you'll find that system gets frustrated because everyone, both the exchange interactions wanted to antiferromagnetic aligned. And you see that because of that, there will be frustration in the system. And in case of frustrated system, the system neither goes ferromagnetic or antiferro, rather it have some kind of a spiral behavior, and and you'll have this kind of a arrangement the spiral-like behavior arrangement and this. And I'm showing the Hamiltonian of this system here. And you see that the dimerization is only in the nearest neighbor. Uh, and this second part is J2, which is next nearest neighbor. I'll be using a term alpha, which is just ratio of J2 by J1. And this is very interesting that this simple model have explained zillions of compound, especially one-dimensional compound. And some of these are like a very recent compound, which is like shown here. And like every month you'll find some new compound, and most of those compounds can be fitted with this model. And there are lots of interesting phases. So rather I would focus on the phase diagram here today. You see that you have the beautiful phase diagram in J1, J2 parameter space. If you have J1 dominant, you see that it is anti-ferromagnetic gapless state. If you further crank up the phase diagram, and then if you further crank up, you go to the incommensurate gapped spiral phase, decoupled phase. But if you start with, I mean, if you go in this quadrant, this is where the ferromagnet, and there's a big reason where the system, you see that the system, if this becomes very weak, it will behave as there are two spin chains independently kept. Okay, and if you keep cranking up from this direction, the J2, you go from ferromagnetic state, and then incommensurate gap phase, and so on. Okay, and finally you land up, if J2 is very strong, then you are in decoupled gapless phase. Okay, so what happened to the let's talk about the effect of delta uh, when and on the singlet triplet gap, and for different values of alpha. Alpha is J2 by J1 ratio. And you see here that for HAF spin half system have a gapless spectrum in absence of uh, of the, and in fact this gapless spectrum opens a gap once you have the finite delta. Okay. So, and you see that the variation of uh, delta for different J2 by J1 ratios are shown here. And you see that as we keep increasing the alpha, the gap, the, the dependence of ST gap on delta decreases. Okay, the exponent decreases. And and all of us know that the MG point has the highest singlet triplet gap, and it goes as delta to the power 0.642, and gap is doubly degenerate, and this is doubly degenerate because you have this two singlet dimers and these two are connected by the rotational symmetry. Okay, so how to model the spin spiral transition? So dimerization is, you know that dimerization is because of the electronic degree of freedom, or the fluctuation in the electronic degree of freedom, whereas the dimerization is opposed by the atomic vibrations. When you heat the sample, the atomic vibration are going to try to dominate, and there will be competition between these two. And at the equilibrium condition, your your this thing your this condition should be valid. Here the epsilon d is your stiffness constant, and the a is your free energy, and lambda is dimerization, as you know. And we can see that these crossing points are the equilibrium delta, and if you plot these two, and these crossing points are going to give you the equilibrium dimerization. So when you plot this equilibrium dimerization as a function of temperature for different uh, ED, and you see here that as you keep increasing ED, this value is going to go and decrease. And from this, you get the equilibrium delta, and then calculate the this ratio, which is the singlet triplet gap at zero temperature, and finally this is the ratio as a function of temperature. And you see that your gap is changing because your system have a change in the dimerization. Okay, so the gap start decreasing as you decrease the temperature, because your dimerization is also decreasing with the temperature. Okay, so this is what is happening here. And in fact, these are the experimental data, and this is red line is our theoretical calculation. So here again, I'm showing the modeling of the speed transition. This is for TTF, the metal organic compound. You see, it beautifully fits the whole experiment. And this is for copper germanate. Again, same thing. I mean, these two are from two different experiment, and the black one is from other one, and other one is from the different. I mean, there is a discrepancy in the sample, but you see, ideally, if it is from same experiment, it is the full reason. CV is again shown here, and you see that it shows the behavior, the experimental. It almost mimic the experimental characteristic. These points are the experimental values, and this line is uh, our theoretical calculation. Again, I'll go to the INS data, and here you see you should compare this one and with this one, and see the intensity is corresponding to this intensity what they have plotted here, and you see that this is fantastically matching with the experiment in the whole reason of the whole dispersion curve can be like a reproduced using this simple theoretical model. In summary, we discussed the experimental data of this copper germanate and also bis dithiolene metal complex, and both the systems shows speed transition. And we also showed you the scaling of the singlet triplet gap as a function of alpha or G2 by G1 ratio. The magnetic properties of both these can be explained by simple frustrated spin chain, even basically in whole temperature regime. And uh, I'll thank my collaborators, Professor Sosh from Princeton University, and these two, Sudeep and Daya, has done the whole work. And thank you very much for your kind attention. And I last thank the funding agency, the CRB and SNBO Center.